Well, let me introduce John Gizis, who's going to talk about the Nobel Prize in Physics this year. John is an associate professor in the Department of Physics and Astronomy. He earned his PhD in astronomy from the California Institute of Technology in 1998. Then he did postdoctoral research at the University of Massachusetts, and then worked at Caltech again before joining the University of Delaware in 2001. John is an observational astronomer. He's primarily interested in very low-mass stars and brown dwarfs. These objects can emit photons over most of the range of the electromagnetic spectrum. And so he uses many different kinds of telescopes, including an X-ray telescope. He observes in the near-infrared and the mid-infrared, and has even worked in the radio frequency range. Actually, I stole this from his website. It says, I don't even know what this means. He is proud to be contributing to the LSST project as a member of the Differential Astrometry Working Group and the Stellar Population Science Collaboration Team. So since he's proud of that, I thought I would mention it. He's teaching physics of the 20th and 21st century, typically taken by physics students, but he also teaches courses for non-majors and a special course for first-year undergraduates in the physics major. And remarkably, he writes a nearly daily blog on astronomy research. So if you're interested in the latest updates on what's going on in the field, I can recommend that to you. It's quite readable and interesting. With that, please welcome John Gizis.
Well, I'm glad I updated the web page for the first time in like 8 years in a fit of enthusiasm earlier this year. Today's talk is on the what is really a sort of an astronomy project, which, however, has led to results that are quite interesting and even somewhat surprising, enough so that it attracted the attention of physicists, and so it's been awarded the Physics Nobel Prize. And the summary here will go through it all, but of course it's the discovery of the accelerating expansion of the universe through observations of distant supernovae. And basically the award has been split among 3 people. Half the award goes to Saul Perlmutter on the left. That is the left? Someone's left. And Schmidt and Rees have split the other half. Basically, these are 2 rival teams that were making the same measurements simultaneously, indeed both using more or less the same methods. And in the end, that turned out to be for the best because the results were rather surprising, as we'll see. It was very reassuring to other astronomers and physicists that both groups got the same thing. Of course, these are sort of the leaders of the project who get the Nobel Prize. As you know, the Nobel Prize is only given to at most 3 individuals per year. These are the actual major publication papers of the results, and you can see there were many people involved, right? And of course, this is only the people on the scientists on the team themselves. If you think about it, all of this work depends on earlier work by astronomers and physicists over really the preceding 3 generations. It depended on having large telescopes and cameras that had been built with the support of the US government by many engineers and physicists and astronomers who go nameless. So really we are awarding 3 individuals, but it is an achievement sort of the field. And so to talk about this, obviously we need to explain what we mean by the expanding universe. We're going to have to talk about why one would use supernovae and what they would have to do with the expanding universe. And then finally we'll talk about the results, which is the actual acceleration of the universe. And when you talk about this, you immediately have to go back to Einstein, which perhaps is the example, more or less, of a great genius individual working on his own, not depending on thousands of people to build a telescope for him. And he developed, during the First World War, the theory of general relativity, which replaced the previous laws of gravitation that had been done by Newton, and which could be used, not only by Einstein, but other physicists over the 1920s, to solve for what the entire structure of the universe might be and how it might change in time and what would happen. And in this theory, what we need to understand from our point of view here is that space-time, or the structure of the universe, is affected by the mass that is in it. And in fact, really not just the mass, but really any form of energy affects it. And so if I can be brave, this side of the equation, and really this is a clever way of writing the math so that this is like something like 10 nonlinear equations that are virtually impossible to solve unless you make a lot of assumptions. Here are our energy contributions or mass, and over there is the curvature of the universe. But after Einstein got this result, which I believe he published in December 1915, he thought to himself whether he might have overlooked something and whether something might be missing. And I thought of a simple analogy to understand both what might be missing, but also why it was controversial to include it. And although it's a very crude analogy. And so I would like you to imagine that you're back in high school, or perhaps even elementary school, and your teacher assigns you a problem. They tell you that you save $1,000 a year for 10 years. And of course, since this is a question being asked in 2011, there's no interest on savings, so you don't have to worry about that, right? And they ask you, what do you have at the end of 10 years? And so I was going to pick on one of my students in the audience, but I decided that would be unwise. And I will simply say that I would have written down the answer, $10,000, right? 1,000 times 10,000. And then the teacher, I guess Einstein himself, marks it wrong and gives you a 0. He says, you have forgotten to take into account that you owed $10,000 before you started this whole process, and so you have nothing at the end. And you can see that you could play this game with any number at the beginning, right? This is sort of the analogy of the constant of integration that those of you who have taken introductory calculus remember perhaps being marked wrong because you forgot to write plus c on it. And Einstein had realized that, in fact, in the same way, and of course this is obviously a loose analogy, we can add an extra term to the equation, which for some reason he gave the symbol lambda, and otherwise was called the cosmological constant. And this represents the energy of empty space, right? So of course we had to account for the mass and energy that we see around us, right? A planet, a star, a galaxy, right? A moving particle of light. Any of those things go over here in T. But let's imagine that empty space with nothing in it is not nothing, but actually has energy. And so Einstein thought of that loophole, and the reason he thought of the loophole was that he wanted to find solutions for the universe in which the universe never changed. It was what we might call static, and so it sat there, it had been the same forever, and it would go on being the same forever, and he thought that this was very elegant. Unfortunately, this eventually would go down in history as a great blunder. Whether he really said it was a blunder or not is perhaps not as well documented as people usually say. But astronomers who began to measure the motions of galaxies found that as you look further and further away, and I've helpfully labeled for you that here, if in 1929, if you measured the furthest galaxies they could do, which were 6.5 million light years away, you found that they were moving away from us at 1,000 kilometers a second, which is, quite fast. And in fact, if you had a good imagination, and apparently Hubble did, you could draw a straight line through this data, right? And find that it looks like the universe is expanding. In other words, things that are twice as far away from us are moving twice as fast away from us. And things 10 times as far away are moving 10 times as fast. It's as if everything started in the same place somehow and expanded outwards. And in fact, Hubble, by 1931, had pushed out to 100 million light years, and by now you believe that the line, which was all based on that data there, in fact is perfectly good. So this is a much more convincing version of what's now known as the Hubble diagram. And of course, for those of you who don't know, the Hubble Space Telescope was later named in his honor. Right? I should add that, however, as we will see, this business is a little bit tough to do, so it turns out that all the numbers here are in fact wrong by a factor of about 7 or 8. So that's, unfortunate. So really, 100 million light years is more like 700 million light years, but we'll leave that be. It was an important discovery. And in the context of general relativity, we should not think of this as just a matter that, some bomb has exploded and galaxies are literally moving away from us at high speed, but this is an animation I found from Ned Wright's website. You see, we all get our information from websites nowadays, right? And here are a bunch of galaxies. The galaxies, you notice, are sort of sitting still, and in this analogy, they're sitting on the surface of a balloon. And so, as the universe expands, even though the galaxies themselves are not moving, the distance between them is increasing, right? Just like the surface of a balloon blows up. And none of the galaxies are at the center of the universe, right? There is no center to the surface of a balloon, right? And so that's the kind of analogies that those of you who are in the introductory astronomy class will have to deal with trying to think about. But for our purposes, you might notice these squiggly things. This is the light that leaves each galaxy, and they travel along, and they go along. And some of the lucky bits of lights will someday land on the telescope, right, operated by a human or at least a computer there. And during their journey, you'll notice that since the surface of the balloon is stretched out, just as the space-time of physics has expanded, the wiggles have stretched out and the wavelength of light is redshifted. Okay? And so the obvious thing one would like to do is that once one manages to measure the expansion of the universe, you'd like to find out, did the expansion of the universe change with time? Right? Was the universe always expanding at the same rate, or was it expanding more slowly in the past, or faster? And in fact, the answer is quite obvious. The universe must have been expanding faster in the past because gravity is only attractive. And that means the expansion should be slowing down, right? I mean, if you took a bunch of balls and throw them in the air, right, as the proverb says, eventually they'll come back down, they'll be slowed down. And even if you had a rocket that was fast enough to go all the way into space, gravity would still slow it down, even if it was fast enough to eventually escape. And so what we would like to do is measure how much mass there is in the universe by measuring how much its expansion is slowing down. And so about 3 generations of astronomers wanted to make this measurement, right? You don't get a Nobel Prize for proposing the measurement. The hard part was actually doing it, right? And in particular, even if we take Hubble's value at face value, 100 million light years or 700 million light years, what you really need to do to see how the universe was expanding more at a different speed in the past is we need to extend this diagram. But that means you have to precisely measure distances of something like 5 billion light years. Because from the expansion rate, we can tell that the universe is 10 or 20 billion years old, something like that. So you're going to have to go back at least 5 billion years to find something interesting happen. The problem in astronomy is it's very hard to measure distances, right? All we see is a 2-dimensional projection of the sky that we take a picture of. And so I'm going to show you, be brave and show you an example of my own research, which is here is a particular field of stars. No one has ever been interested in this particular location on the sky, but we certainly took lots of pictures of it just to be complete. And you can see there's a bright star, there's another star, there's a dim star, there's a dim star, there's an even dimmer star. Which of the stars in this picture are the closest? I can tell you that almost all the stars in this picture are 1,000 or 2,000 light years away, but one of them is only 25 light years away. It's that one there, right? But it doesn't look any different. I mean, the color is different. That's how we found it. But basically, they all look like points of light, right? You have to have some extra information to tell how far away an object is. And in the terminology of astronomers, we like to say that we need standard candles. Because an object can look dim because it's far away, but it could also look dim because it just doesn't give off very much light. Or it could be dim because there's something in between obscuring it, right? As the sun can get dim if a cloud passes in front of it. So you have at least 3 possibilities, and we only want to get the distance. And so we need to know something that's a so-called standard candle. We know how much light it's giving off. That's very hard because we want to do it for something that's 5 billion light years away. And of course, you can't see individual stars that are that far away. Even a galaxy that's far away looks very dim and hard to see, as you'll see in the later pictures. Now here's a nearby galaxy. This is called the PINWHEEL galaxy, or M101, if you like catalog numbers. And you can see there's a blobby thing in the middle with the spiral arms. We might live in a galaxy much like this one. And it's about 24 million light years away. We know that from the work of other astronomers using Hubble Space Telescope. But what's interesting about this image, which by the way was taken in Delaware about a month ago by the students in Physics 469, is that there's actually a supernova in this image. A star in this galaxy has exploded, so there was nothing there before. And suddenly a star that's as bright as really the rest of the galaxy, you can certainly see just from the image here that it's much brighter than all this fuzzy stuff, right, has appeared. And so the idea is that if only we could understand supernova very well, they're as bright as galaxies. We could see them, right, all the way on the other side of the universe, 5 billion light years away. And it turns out that there's at least 2 different types of supernova. And the idea of using supernova goes back at least to the 1960s, by the way. So again, it's not a Nobel Prize for thinking of the idea. Lots of people thought of the idea. The hard part is to do it. And so one type of supernova comes from stars that maybe are more or less like the sun. They go through their evolution. At the end of that evolution, they leave a white dwarf, which is an object that perhaps has more or less the mass of the sun, but it's the size of the Earth. Right? So it's very small and dense. And it turns out that those objects have a problem. If someone were to be so unkind as to drop more matter on them to make them more massive, then every calculation we have says that they will blow up. And they will blow up when they reach 1.4 solar masses and cause a supernova. On the other hand, you can also make supernovae by having very large stars, 10 or 100 times the mass of the sun, and they'll just blow up on their own when they reach the end of their life. And so, by the way, here, Harry Shipman and Judy Provençal and Jim McDonald do a lot of calculations related to this type of astronomy. Stan Owocki does these objects. Those objects, for our purposes, are no good because basically every massive star is unique. The supernovae are very different from each other. They're not useful as standard candles. But the belief is that white dwarfs are all the same, and that these supernovae could potentially serve as standard candles. And here, by the way, is an example of a supernova that was in our galaxy. It's known as Tycho's supernova remnant. So it blew up in 1572. Well, really, it blew up right 9,000 years before 1572, but 1572 is when the light of the explosion reached the Earth. And it was a white dwarf destroyed in a supernova explosion. And we should care about such things because it turns out that if you think of the iron and all the other metals and heavy elements in this room, they were all created in previous generations of stars, some of them in supernovae like this one. Right? So that's very interesting, but we want to get this year's Nobel Prize, so we're going to use the supernova purely as some sort of standard candle. And in order to do that, you obviously have to detect the supernova for the first place. And here's an example of their data back from the day. What you need is a large telescope, so you can see faint galaxies, which has a camera that can image large portions of the sky. Because one of these supernovae, as you can guess from the fact that I'm showing you an example from 1572, per galaxy maybe blows up once per 100 years. Maybe twice per 100 years, right? So you have to have a big image, and all of this image is full of little galaxies. They're hard to see here because they're a little bit dim, right? And somewhere here, you hope that you image it every month, and if you image enough galaxies, one of them will have a supernova that blows up. And in this particular image, it was right over there. Let's blow it up. There's a galaxy. It's not doing anything interesting. There's a galaxy. There's a galaxy. They're not doing anything interesting. But look at this galaxy. It suddenly got twice as bright. Right? It's a supernova. Right? A galaxy itself can't suddenly get much brighter. And in fact, when you subtract the images, you can see it looks like a single star. And if you're really brave and you use Hubble Space Telescope, it continues to look like a star. It's a new supernova, and there's the galaxy itself. So we, or at least the teams, could measure these supernovae even billions of light years away. And so if you could only understand how much light they were giving off, their intrinsic luminosity, you could get the distance right away. And here's more pictures from Hubble Space Telescope, just to show you there's a supernova, there's a supernova. Right? The pictures don't look as good as M101, because even with Hubble Space Telescope versus a telescope on sea level in Delaware, right, you still lose out because the things are so far away. But nevertheless, you can still measure them. And so the question is, are they standard candles? And unfortunately, as people debated this thing from the 1960s to the early 1990s, although everyone said that they should be standard candles, it never quite worked out that well. Here is the measurements of the brightness of a whole bunch of different supernovae. So, for example, one supernova is in green, right? There's its data points. Over the course of about 20 days, you see it gets much brighter, and then it becomes very dim. On the top, in another color I can't really describe, I guess it's pink, there's another supernova. You notice this supernova is much brighter. It's higher up on this graph, right? In fact, the variation of these supernovae is a factor of 3, which means the error in distance would be the square root of the factor of 3, which would be 70% errors in the distances, and that's terrible, right? You're not going to measure changes in the expansion rate of the universe if you're making 70% mistakes, right? But the good news is that a variety of techniques were developed which showed that all of these supernovae were controlled by a single parameter. And so if you look at this carefully, you'll notice that the dim one falls off very quickly, and the bright one sticks around longer. And so if you can measure that, you can correct them, and you find that all of the supernovae are then the same once you apply this single correction. And then the supernovae are all the same to within 15%, which means you can measure the distances, to 10%, and you're golden, right? And so it was just a matter of then doing the project, showing that you could find these supernovae, measuring them accurately, and they got some results, which I'm going to show you some different versions of the plot, but here it is. What they found was that as they observed more and more distant supernovae, that is, ones whose light on the way to us had stretched out here by 50%, there by 80% over the original value, so they're very far away. There's the supernova. They look dimmer and dimmer and dimmer on this plot, right? They look dimmer and dimmer and dimmer. But what's surprising is it doesn't go the way anyone expected. In fact, the supernovae are dimmer than they should be, even if the expansion were not slowing down at all, right? And they're much dimmer than they should be if the expansion were slowing down by the amount of dark matter that some people thought there should be. In fact, the brightness of the supernova indicates that the expansion is not slowing down at all, as I argued must be the case, but that in fact the expansion is speeding up, right? And the way that astronomers certainly at first interpreted this is that there is a cosmological constant after all. Einstein's blunder was a blunder in the sense that he missed his chance to predict that the universe is expanding, but in fact he was right. We had to take into account the energy of empty space. And these supernovae that we're measuring are from like 7 billion years ago, right? This is the rival team's plot. This is from the high Z supernova team. And so basically, if the supernovae lie in the cyan or blue region of the diagram, then the universe is being accelerated. If it's in the purplish thing at the bottom, then it would be recollapsing, that it would be slowed down by gravity. And over here, we have lots of gravity slowing down the expansion, but it's not enough to stop the universe. And you can see that after the inner part, which is hard to tell, oops, these guys are clearly in the blue region. The universe is being accelerated. You can tell by the fact that there's big error bars on these points, and that it's not the most obvious thing when you first glance at it, what region it lies in, that this was not a eureka moment. Both of the teams have been asked about how did you realize this discovery happened. And they said, well, we knew that the technique was working when we were able to measure the supernovae, but we assumed that there were kind of calibration issues, right? That all we, oh, well, we're probably measuring it 10% too bright. Let me, check what dials we can adjust and what mistakes we're making. And it took them a while to realize that there was no mistake. In fact, the universe is accelerating. And one way you can plot this in the modern viewpoint is that you can plot the contribution of the cosmological constant to the energy density of the universe. Remember, this is the energy contribution of empty space, right, where there's nothing there, versus the contribution by actual matter. And what the supernovae tell us is that the truth lies somewhere in this blue diagram, right? And you can tell from the slope of the figure, those of you who like math, is what they're really sensitive to is the difference between the two, right? And so they get an upward slope. So they can tell there must be a cosmological constant, right? And if you want to have more matter in the universe, they say, well, that's okay with our measurement, but we have to add even more cosmological constant. By a happy chance, there's also a series of measurements that are getting basically their own set of Nobel Prizes on the microwave background radiation, which can strongly constrain the sum of the two, which means you get a diagonal line like this, that the truth lies somewhere in this green region. And it's not hard for you to see that where the blue region overlaps and the green region overlaps, I mean, this is like playing Venn diagram, right? You can see that the truth lies over there, right? The universe is 70% cosmological constant and 20 or 30% matter. And then there's another set of measurements from clusters that are only sensitive to the matter, and they say the truth is there. And the good news is it goes through the same point that the other ones did, right? So we're very happy. So the bottom line is that these measurements lead to a number of conclusions, which range from mundane to truly surprising and worthy of the Nobel Prize. One is that the universe is 13.7 billion years old, right? We now believe we know that quite precisely. And we know that about 30% of the universe is matter. It's perhaps a little unfortunate that we can't see most of that matter, so we call it dark matter. But it's not, it's some sort of particle. It's not a proton. It's not an electron. It's not a neutron. It's something else that the physicists have yet to discover, but it at least acts like normal matter. And then 70% of the universe is Einstein's cosmological constant. Or more generally, because you can imagine that physicists have been at work for the last 80 years since general relativity was discovered, it could be some other form of dark energy. Right? And there are a number of theories that have been proposed in which this energy might change with time, right? Or change with density. And so empty space as energy and negative pressure is causing the universe to expand more and more rapidly. So if you think about it, right? What happens is you have two galaxies, and as the universe expands, the space between them doubles. Now you have twice as much empty space, which means you have twice as much dark energy. The dark energy, it turns out, pushes things apart. That makes the galaxies expand more. Now you're going to have 4 times as much empty space. You're going to have 4 times as much dark energy. And so unless there's something we don't know that makes the dark energy go away, the universe will apparently expand forever. And will not merely expand forever, it will keep accelerating apart. And indeed, in some versions of the theory, in the future, astronomy will no longer be possible again, and we will not be able to see any galaxies at all. They'll all be so far away that light can't reach us. Right? And things will, right? Our observable region of the universe will close back in on us. Perhaps. In any case, what we don't know is why should there be dark energy? Why should empty space, right, have this property? It seems like a cheat, like your teacher, saying that your savings is wrong because, we're just going to apply some extra constant to it. So what is it? Does it change with time, or is it really a cosmological constant? That's exactly this. We don't know. And unfortunately, it'll be very difficult to get at this any other way than through astronomy and these indirect measurements, right? And the reason is that the energy density of this dark energy turns out to be 10 to the minus 27 grams per cubic centimeter. Now, those of you who don't remember the metric system that well, remember that water is 1 gram per cubic centimeter. Well, we could measure water, that's fine. 1 single atom in a cubic centimeter would be 10 to the minus 24 grams per cubic centimeter. So if you did a lab experiment and you had a single atom in your device, it would outweigh the energy density. And we certainly can't make vacuums that consist of only a single atom, right? We don't have vacuum pumps that are that good. So it's somewhat baffling to know how we're going to make progress on this, other than trying to measure the details of supernova with the LSST and WFIRST and other proposed space experiments in the future in great detail. So it's a terrible puzzle that something is missing in physics, something that describes the properties of empty space. And it's very hard to know what to do with it. But that's why they got the Nobel Prize, because it's really pointing to some fundamental new physics. So thank you.
Any questions for John?
Stupid question. If matter exists and the universe is matter, can you say wherever there is matter, there's a center of that matter?
Oh, yes. Well, certainly, we would locally, say that the center of the solar system is the sun, right? I mean, in terms of that would be the best way to approach things. Although, if you're perverse, you could certainly calculate it as the center of the universe is, Delaware, right? And then have to describe how things go around in a very complicated way. For practical purposes, we would talk about a center of our own galaxy, right? We would talk about the fact that our galaxy is part of a local group, and that local group is falling in towards the Virgo cluster, which is a larger, collection of galaxies that's very near to us. So certainly for practical purposes, there are things that you might be able to think of as the center. But in terms of a true center of the universe is saying this is where the Big Bang happened. The Big Bang happened everywhere, right? The Big Bang happened here, and it happened in that distant galaxy 6 billion light years away, right? All of them were, in some sense, there is no center from that point of view.
There is no center of the expansion.
There is no center of the expansion, and that is obviously very hard to visualize. So the space between all the points is getting larger, right? But of course, for us to think about that in any normal way, we need an additional dimension, right? So the balloon obviously has a center, right? But at least in the context of these theories, that's all an analogy. all we can really say is the distance between everything is getting bigger. But it's not fair to say any particular point is the center.
I imagine that data has been looked at awfully hard, but I noticed that the early points are on the line and the distant points are away and nothing in the middle.
Yes, that's true.
Yes, maybe something's going on.
So you'll notice, strictly speaking, oh yeah, sorry. Where are we going for the, we've lost it.
I think maybe.
Okay. The nearby galaxies describe a straight line, and under basically no theories do we expect there to have been much acceleration, at the present time, right? And furthermore, if we did, there'd be something it wouldn't look like a line, right? There'd be something really weird going on. So the supernovae are actually calibrated to that straight line. So we measure the local expansion using other methods like Cepheid variables, and then the supernovae are actually in galaxies that we think we know the distance to, and we put them on the line, right? And so it is true that there's a great deal of work, and of course progress since then, in filling in all the different redshifts. So you want to get to higher and higher redshifts, but at the same time you really want to fill it in, because any individual data point you saw had a big error message. And that's why both groups' work were important. So the one group published first, but with a single supernova at high redshift. Right? And then a few months later, the other people said, we have 4 or 5 at high redshift, although they're, and then, right? And so the contributions of both are sort of viewed as equally important, and but they were really working in parallel.
I remember seeing that first plot, and it was just 1 point off the line. I thought, this guy's nuts.
Yeah, and especially, the reputation is, you have a nutty result that appears in Nature. They probably rushed it and made some mistake, right? And that's why the second group to publish is viewed maybe as equally important, without criticizing anyone, right? Both groups did, obviously did it right.
Did the two groups interact with each other prior to the publication?
I think they were aware of each other's work. They'd been publishing along the way, right? In fact, the one group that published second has some pointed remarks, if you read the paper, about, about the various things. So they all developed their own methods and worked on it. So they were, to a certain degree, aware that they were both making the same measurement, but they didn't know each other's results. And so they independently got the same result, I think is fair to say.
So if the first group had decided to wait a little longer and collect a few more supernovae, how long would they have expected before they got the second or third one out in that range? How many more months?
Oh, by the next year, they had many more. Yeah, so, it was a matter of getting things really working, right? Because you sort of set up a factory, right? You set up a factory in the sense that you can image this much of the sky. You've learned how to schedule everything, right? I mean, in some sense, there's actually quite clever papers about how to schedule these things, in the sense that you need many telescopes at the same time. And normally, astronomers don't really want to give all of their best telescopes to a single person on demand, right? And so they had to work out how to schedule these things, right? Because, of course, obviously, you'd want to look at brown dwarfs with them, right? Yes, these are observations with optical telescopes. In the future, as you go to higher and higher redshift, the light will have been redshifted into the infrared. And so that is what drove the cosmologists, the extragalactic astronomers, and everyone to back this James Webb Space Telescope, and why James Webb Space Telescope is primarily an infrared telescope. Because you could not do this measurement, say, at redshift 2. Well, maybe there won't be any supernova at redshift 2. But at redshift 2, all the light will be in the infrared. So it'll be impossible to make the measurement with a ground-based telescope.
Use the word expansion. Could you substitute for expanding the universe, calling it less dense, and then try to analyze it in terms of what causes things to become less dense?
Yes, that would be, that's probably an equally valid way to look at it. So the density of the universe is going down with time. And then you would still have Einstein's same equations to describe this, right? The key point is that let us say that you either have to have the universe expanding or it has to be contracting. It's essentially impossible to have it perfectly in balance so that nothing happens, right? Einstein had to put in a repulsive cosmological constant, but even that would have been unstable. Right? You move one galaxy a small amount, and everything would start to collapse or expand. So in the sense that things will the density either has to decrease or increase with time. right? Now, of course, it used to be, especially if you took a cosmology class 20 or 30 years ago, many people liked the idea that the universe had a lot of matter in it, so it would expand, and then it would eventually stop, and it would contract again. And then the opposite of the Big Bang, was obviously called the Big Crunch, right? And then you might even imagine that maybe that would turn into a Big Bang again, right? And then you never had to worry about what began the universe because it would just keep doing this, right? But unfortunately, it appears that we don't live in a universe like that because the universe, from all our measurements, will expand forever. It will not crunch back down again. If there were more matter, it would turn around, so to speak.
Any last questions? All right, Stacy and John will be around at the end if you have anything you want to ask them one-on-one. Let's thank all the speakers today.